this example, we are going to look at the magnetic field inside and outside a thick wire. A thick wire. So let's draw our wire. So here it is. It has a big cross section. Let's call it, give it a radius of r. And we're going to have the current coming at us. So here's a uniform current density represented by a whole bunch of vectors that are pointing at us. And for this, we're going to use Ampere's law. Ampere's law, which is a bit like Gauss's law for magnetic field. So we're going to calculate a loop here of B dotted into dl, some path along our loop that we get to pick, and that's going to be mu naught times the charge enclosed, or excuse me, times the current enclosed. Okay, so for the first part, let's calculate our field inside the wire. Inside the wire. All right, for that, we're going to do a little loop. And if our current is coming towards us, all of these little magnetic fields are all these little pieces of the current are producing magnetic fields that curl around counterclockwise. And so our loop is going to point in the same direction. And so that means that the left-hand side of Ampere's law, B dotted into dl, if you choose loops that are pointing in the same direction, parallel everywhere, then this dot product simply becomes B times dl. And there's a cosine term that's 0, which is a 1, so we can ignore that. And through our loop, by symmetry here, B is going to be constant. So we're just walking around a little loop inside our wire. And so that's going to be B times 2 pi r. Because if we carve out an entire loop, a circle here, we're going to have a circumference that we've walked through. And that is going to be mu naught times the current enclosed. All right, so we're done with the left-hand side here, which is great. Now let's look at the right-hand side. How do we figure out how much current is enclosed? Well, for this, you should think of, you can almost think of pizza if you want. We want to figure out how much of this thick wire we've enclosed. So we're comparing the small circle here to the larger one. And if we want to, we can set up a fraction, right? The current enclosed over, let's call it the total current. That would be for the whole wire, which we'll do in the next step. Well, that's going to be a ratio of areas. So pi over big R squared for the thick wire, and pi times little r squared, where r is less than r in this case. And so the current enclosed is going to be related to the square of little r divided by the square of big R times the total current. And so let's combine all these terms together. So we have a B times 2 pi r. It's a little r. Is equal to mu naught times little r squared over big R squared times our total current. And we can factor out a little r and bring the 2 pi over. And so we get that B, and this is inside the wire, inside the wire, is going to be mu naught over 2 pi. We have an r times an I total up top, and an r squared term underneath. Okay, so that is our magnetic field inside the wire. Now let's see what we can get for our magnetic field outside of the wire. So in this case, R now is going to be greater than our radius of the wire. And so this is a magnetic field dotted into a little piece of the loop. Right, here's our Ampere's law again. For the same reason that we discussed in the first part, this ends up being just B times dl, which is going to be B times 2 pi r. And now the current enclosed, well, we don't have to worry about any scaling. The current enclosed is just the total current. And so this is mu naught I total over 2 pi r. And we are done. Now, if we compare that outside term to what we got inside we got mu naught I total times r all over 2 pi times r squared. Well, you can see that at little r equal to big R, these two terms end up being the same, right? Because I can plug in a big R over here on the outer term and get mu naught I total over 2 pi r. And on this term, I would get mu naught I total times r, big R now, over 2 pi r squared. Those terms cancel, and everything else is the same, so it checks out at that boundary condition.